Okay. Okay. All right. Let's get going. Starting with recap. Walter. Yes, Eric. What are the common steps in extracting fat-soluble vitamins, Justin? Yeah, what are we saponifying? What is usually soluble in organic solvents? Yes. So when you saponify them, you make them more soluble in the aqueous phase, and what remains are the vitamins, and they can be extracted by organic phase. What are some precautions during sample preparation and why, Emma? Prevent heat so it doesn't degrade. Lucy? There you go. Oxygen. And another one, there's one more. So light, heat, oxygen. Chelating agent you add to prevent chelating agent. I was thinking he was gonna say Dr. Shilani, and I was like, what? No. pH. Okay. Um, so we haven't gotten to that in lecture, but you all had labs. So using the endophenol assay for vitamin C, what do we do if we want to measure both forms, including aldehydo? Uh, Peter? I would add a reducing agent. So if I have aldehydoascorbic acid, which is still bioavailable, and I want to quantify it, I will reduce it back to L-ascorbic acid, and then I can quantify it. Okay, cool. So we talked last time about different types of analyses. Bioassays using in vivo methods, microbial assays, and then chemical assays. So for bioassays, usually the ones that are available are for vitamin B12 and vitamin D. Vitamin D is also is an official method using animals or rats, but it's also you can detect it, both of them, you can detect it by different methods. Vitamin D, vitamin B12, you can do microbial assays, and vitamin D, there are several AOAC based on HPLC analysis. But in case of bioassays, it's a feeding trials using animals and then sacrificing them. So if we look at vitamin D specifically, it's a method based on calcification of the bones. So we call that line test. And what happens is you get the rats and then you have a depletion phase. I mean, you feed them a diet that doesn't have vitamin D. So you deplete their system from vitamin D, and then you feed them, you create a standard curve. So you feed them different levels of vitamin D, known concentrations of vitamin D, and then a group gets fed the unknown sample, which has an unknown amount of vitamin D. So, and then the animals, after a certain period of time, they get sacrificed, and then a certain bone would be selected and calcification is measured. So it depends, it's correlated, so it has a direct correlation with the amount of vitamin D that was consumed. So you would construct a standard curve based on the known vitamin D that was consumed, and then you would determine the unknown concentration of vitamin D in the food sample. Microbiological assay, they're simple. You grow organisms with and without the vitamin, and because vitamin is needed for the growth, then the growth of microorganisms are proportional or is proportional to the amount of the vitamin that you have. So, and you measure that growth by measuring turbidity or acid production or the actual weight or respiration take up of oxygen. The two vitamins are commonly measured that way is niacin and folate. If you look at the folate example, so folate can be conjugated to multiple units of glutamate, amino acid. So in order to and it's conjugated with glutamate and also associated with proteins and carbohydrates. So in order to determine it, you would use a tri-enzyme digestion. It's an AOC method, and then alpha amylase will digest the starch, protease will digest the protein, and then the conjugase will break off glutamate. And then it will be free for detection or take up by the bacteria. And the bacteria that is used is Lactobacillus rhamnosus, is a common one. And then in this case, you just look at turbidity. So you would measure transmittance at 550 nanometer. So that's how that's determined. Now for fat-soluble vitamins such as A, E, and D, they all can be performed using HPLC methods. So the chemical methods for these is basically you saponify, you extract by organic solvent, and then you run HPLC, and then the detection can be either UV detection or fluorescence detection. So it's just a general procedure that you're required to know. Okay, so the vitamin C, which we have analyzed in the lab on beverages or in orange juices. So it's the dichloroendophenol method. It's an official method for fruit and fruit products. It's based on the L-ascorbic acid, which is the reducing form. But L-ascorbic acid can be oxidizing as well, agent. So if you know in flour, they fortify with ascorbic acid. But when you mix the flour with water, there's water and you're incorporating oxygen, you're forming aldehydoascorbic acid, which is oxidizing agent. And then it oxidizes the SH groups to form SS linkages. So if you hear, don't get confused, L-ascorbic acid is reducing, but it's added to flour to act as an oxidizing agent once it's oxidized itself. Okay, so usually people confuse that as like, is it reducing agent or is it an oxidizing agent? But in this test, it relies on the L-ascorbic acid being the reducing agent, which reduces a dye, which the dichloroendophenol dye is reduced. And since it's a redox reaction, the dye oxidizes the L-ascorbic acid to aldehydoascorbic acid. And then when the dye is reduced, it goes from a pink, or you've seen it as a dark purplish color, to colorless. And when all L-ascorbic acid is oxidized, there's no more reduced form. Another drop of the dye turned your solution or your beverage pink. And then we use the volume of the dye to measure the amount of vitamin C using the titer. It only measured the L-ascorbic acid. So we used the titration, and then we looked at the endpoint as the determination. But if our sample is colored, we won't be able to see the change in color to pink. What would we do in this case?
Could measure the change in fluorescence?
Yes. Then you can do a spectrophotometric analysis by measuring at a specific wavelength to detect a change in color. Yes?
So why can't you just take orange juice or something like that? Why couldn't you just dilute it until the color's not as strong and then just test it then?
What if it is grape juice?
Well, I mean, add
Or strawberry, or something that already pink? Huh?
Could you just dilute it?
And then it will be insensitive. Your assay will be insensitive. Yeah?
Wait, what did you say again about the aldehydoascorbic acid? You said it was a reducing agent, but it's used as an oxidizer?
It can be. I mean, I just wanted to clarify from a chemistry perspective. You hear that flour is use ascorbic acid as oxidizing agent, right? If you hear that it's used as oxidizing and now I'm telling you it's a reducing agent, you're going to be confused. It will be oxidizing agent once it's mixed with water and oxygen when you're kneading. It becomes aldehydoascorbic acid. In that form, it's oxidizing. Yeah. So it depends on its form. Yes, Carmen. Oh, good questions. Yes.
Could you use a different indicator if you had a different colored solution?
We don't use an indicator. We're using a dye. We're using a dye. The dye is either it's in the oxidized form. It gets reduced. It changes color. Yeah. Yes.
You said we add reducing agent to prevent it to oxidize, but if we add reducing agent, how can we measure how many amount of original ascorbic acid? Because it's still reducing agent.
If you add a reducing agent, you can do with and without a reducing agent. So you can do the titration without a reducing agent, and then do the titration with a reducing agent, and then the difference would be the reduced form and the non-reduced form. Good question. That was the next question coming up, I think. So this is the reaction. That's your ascorbic acid, which is in the reduced form. And this is the dye, which is sometimes I say blue, sometimes red, sometimes pink. I'm not making up my mind. Dark purple. And then the ascorbic acid will be oxidized, and this will be reduced. You get colorless. So what do we do if we want to measure aldehydoascorbic acid? We add a reducing agent, and then we measure the total ascorbic acid in two forms. And then without the reducing agent, you'll get the reduced form. So you'll have the total and you'll have the reduced form. The difference will be the actual amount that was in the dehydroascorbic acid form. Okay? So with the reducing agent, you get the total. Without, you only get the L-ascorbic acid. The difference, you get the aldehydoascorbic acid. Okay. There's another method that you can use to determine vitamin C, which is a microfluorometric method. In this method, actually, you want to oxidize everything into aldehydoascorbic acid. So you add an oxidizing agent to convert L-ascorbic acid to aldehydo. This will react with phthalindiamine, okay, to form a fluorescent, and then you measure, in this case, you're measuring both forms because you're converting everything to aldehydo. So you're measuring the total ascorbic acid that you have. So you can also run this assay with and without oxidation, and then you can get the original amount of the aldehydoascorbic acid and then the total. Yes, Stephanie? Well, it depends. This is an official method for all other foods. The other one is specifically for fruits and fruit juices. That's the official method. But that doesn't mean you cannot. I think for gummies, what did you use, Billy? Yeah, because gummies are basically what? Fruit juices?
Sugar.
No juice, just sugar. Yeah, well, water and stuff, then you can use the other one. Yeah.
I'm going back to Lynn's question. If you had reducing agent and then the aldehydoascorbic acid is reduced back to L-ascorbic acid, but there's still reducing agent present in the solution?
That's why you run a blank.
Okay.
So you run a blank with just the same amount of the reducing agent that you used for the L-ascorbic acid, for the aldehydoascorbic acid. So that's why, that's a very good question. Whenever you add anything to your reagent, you will add it to a blank. In the lab, we ran a blank to see if there's a reducing agent from somewhere else. So usually, you would add just a little bit that would be taken up by the aldehydoascorbic acid. And then you run a blank side by side to account for that. Good question. Was that your question, Lynn? Both. Okay, I'm glad it's now complete. Anybody? I saw hands up. Okay. All right, the last two that I'm quickly going to talk about are the two vitamin Bs, thiamine and riboflavin. So these are extracted using autoclaving. I mean, you need heat in the presence of acid. They get extracted. One, you would, because thiamine has phosphate esters, use enzymes to break those phosphate esters. And then you use chromatography to clean up your sample. And then you oxidize thiamine to thiochrome, and you measure fluorescence. So that would be the excitation and the emission wavelength. EX is for excitation, and EM is for emission. And then riboflavin, you add, you oxidize interfering material so that when you measure riboflavin, you're not measuring anything else that might absorb or fluoresce at the same wavelength. So that's it. Of course, the methods are more involved, more detailed. You can find them in the AOAC method, but this is, I just want you to know the general idea. Okay. So, vitamins, we're done. Any questions? We had very good questions today. Good. Minerals. We have done mineral analysis before, and now you're going to say, why are we doing it again? We did the AA. The AA and the ICP, inductively coupled plasma emission spectroscopy, was only one method out of several methods, well, two methods out of several methods you can use to determine minerals. So today we're going to talk about other methods for mineral analysis. Like always, why do we care? Why is it important, Peter? Yes? Emma?
So you can make health claims?
To make health claims when we fortify?
Like lead poisoning and other chemicals?
Yes, lead poisoning, heavy metal. What else?
Lipid oxidation?
Lipid oxidation, presence of metal. Yes. What else? What happens when you refine wheat flour and you end up with white flour? What do we lose? A bunch of minerals. We do. And then there is the enrichment. College board question. What's the difference between enrichment and fortification? Bailey. Huh?
One of them is like added back.
Yeah, which one is which?
Wait, that it's enriched. What are the two things?
Fortification.
Fortification, isn't it?
Y-
I mixed, never mind.
Mixed up. Ted. Go ahead.
Fortification is when you add something that's not already in there, so like vitamin D in milk.
Yeah.
And then enrichment is when you add it back.
Yes. Okay. That's a good college bowl question. All right. So enrichment is when you refine the flour, for example, you have to add back. Let's say you lost some of the iron. You have to add back the exact amount of an iron to match the exact amount of iron that is in the whole wheat. So that means processing will lead to losses, and then you need to make sure that you put them back, and then you measure to make sure that you have added to the extent where there should have been. Another important one, minerals in water, has to do with water quality. So those of you that are doing project and water is an ingredient, what tests do we do that are related to water quality? Other than Peter. Just because for variety, yes. Hardness. So calcium and magnesium are the two minerals that will contribute to water hardness. And a high amount of those will lead to cloudiness, for example, if you're using the water for beverage application, then your beverage would be cloudy because of the presence of these. Another thing, it will impact the textures of vegetables. If you are washing and blanching and doing all the processing with water, it will impact the texture of your product. Iron in water?
Depends on your source.
Yeah, Haley? Pesticides, but that's not minerals. Yes, we do measure pesticides for water quality, but we look for heavy metal. So we don't want to have any heavy metal that might be leached from the soil into the water. We don't want that to be in our drinking water. Yep. So here they are, nutrition labeling, fortification versus naturally present, processing effects such as refining or water quality when the water contains minerals and what that impacts. So for nutrition labeling, what are the current minerals that are on the label, Molly? One of them is iron. Now it's potassium, yes. Calcium, and there's one more. Sodium. So currently we have the sodium, calcium, and iron, and potentially whenever that's going to be applied, you'll have the potassium. So there are different categories of or classification of minerals, and that's based on how much our body requires. So some we require in larger amounts, like macro elements, others in trace amounts, and then others we don't want them. They're toxic. We don't want them in any amounts. Arsenic, something the body needs, for example, trace amount, very small amount, even nano trace amounts of arsenic, but large amount of arsenic becomes toxic, for example. So the analytical methods, we already covered a chapter on AA and ICP, and we use those when we really have lots of samples to analyze and several minerals to analyze. We do the ashing and we go through the procedure. Sometimes you only want to measure salt or calcium and a certain amount of food products, and you don't have access to either. There are ways to do it, simple ways to do it. Titration, colorimetric assays for phosphorus, for example, titration for calcium and NaCl, salt, and ion selective electrodes where you can measure actually some ions such as salt as well is used. Like instead of pH meter, it would be an ion selective electrode. So you have to have some consideration while you're running the assay or while you're preparing your sample. But in order to know what considerations we have, let's look at the nature of the analysis. So some analyses are based on complexometric titration, such as the EDTA, and I'll give you an example when we use it for calcium. And precipitation titration, such as the Moore for salt, and these both do not require ashing. So we do not need to incinerate all the organic matter and solubilize the minerals. Whereas when we're doing AA, ICP, we do need to ash. Galvanometric assay, because of interference and measuring absorption, we do need to ash. And in some cases, the electrode, use of ion selective electrode, you need to also have a clear solution, and you need to ash. What are some considerations when we are preparing the samples? You think? We are going to mill the sample. What could happen during milling of a sample? Contamination. So we need to be aware of contamination due to processing of the sample, or contamination from glassware, or contamination from reagents that we're using. So one way to deal with that is running a blank. So the gland goes through the entire process similar as your sample. Interferences, so we have to control pH. I'll give you an example of pH. For example, when we are determining calcium using EDTA, we really need a certain pH for the reaction to work. Temperature is also controlled. Sample matrix, where you have interferences from other components in the sample. So, and this time, when you have really complex sample matrix, you prepare standards using the same sample composition. Whatever is in the sample, if you can match it in the standards. Or you spike the samples, or you do your standards in the samples, like the standard addition method that we talked about in spectroscopy. So the EDTA complexometric titration, this is specific for calcium and magnesium. So the principle of it, we're going to titrate a sample with EDTA. So EDTA has affinity to calcium and magnesium. So it can bind calcium and magnesium, but it will only bind calcium and magnesium at really high pH. This is an example where we have to control pH. At low pH, the binding sites of EDTA become protonated. So if they're protonated, they won't be able to bind any positively charged calcium or magnesium. So that's why the pH needs to be high in this particular reaction. With the sample, you add an indicator. This is how it works. So this indicator here will change color from blue to pink when it binds to calcium or magnesium. Let's say bind to calcium in this case. So, however, when you have the indicator in the sample, it's going to bind to the calcium in the sample. When you titrate with EDTA, the EDTA has higher affinity to calcium than the indicator. So the calcium will go from the indicator to the EDTA. Okay? And the more you titrate, more calcium will be displaced from the indicator to the EDTA. And eventually, when all the calcium is displaced from the indicator by the EDTA, the last drop of the EDTA, that is, the color will change from blue to pink because the indicator no longer is holding on to the calcium. So you can do this titration to determine the amount of calcium, and it's also, you have the AquaCheck test strip. This is specific to test the water hardness. So these will be impregnated with EDTA and the indicator. Okay. So another method for titration is when you are determining salt concentration, and there's the more titration is the most common, and it's forward titration. What we mean by forward titration is that you titrate directly with silver nitrate. So you have your NaCl, so the chloride in the sample will react with the silver and give you silver chloride. When all of the chlorides are bound, the next drop of the silver nitrate will react with your indicator, chromate indicator, and will give you an orange precipitate, and that would be the end of the titration. So it's very simple, straightforward titration. Vollard titration is another form of titration used for salt, but it's a backward titration. It's backward because instead of titrating with silver nitrate directly, you add excess. you mix silver nitrate, you add directly to your sample, and some of it will react once everything reacted, well, once all the chloride reacted with some of the silver nitrate, the excess, the remaining silver, will be titrated with potassium thiocyanate. And then you will have ferric ion in there as an indicator. So the silver will react with the thionate, and then the next drop, when all the silver is reacted, then the next drop will react with the iron and will give you a red precipitate. And that would be the end of the reaction. Why do we want to use the backward titration when there is a simple forward one? There is no reason. There is no reason really. They both have been developed. You can use either. Depends on the preference and what the lab has been used to be using. So there is no specific preference. So there's also test strips. We call them quantap chloride titration. They're based on more titration, so they're impregnated with silver and the indicator. And then the change in color is converted to the amount of salt. It's an AOC approved, it's rapid, and it's accurate within 0.3 to 10% salt. That's the range, the working range for it. And the accuracy is plus and minus 10%. Okay, so I was gonna, don't get too excited. I was going to stop here, but I'm not, since I still have time. So I will go over to this. Since this is based on salt, I'll skip over what I wanted to talk about left in this lecture and have you work on this for a +2. And we'll work on that for the remainder of the time. Oh, yeah. But I don't have my, yeah. 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 I would like you to work, not chat, please. Yes, Ted. This week. I'm working on it. I'm very close. So in this case, we're using Vollard titration. And I put the reaction up there because you need to remember the reaction in order to think about this. So everything is, I'm going to give you just a hint, 1-to-1 mole, right? It's 1-to-1 mole. So 1 mole of silver will react with 1 mole of chloride. And I think you need one more thing, which is What's the molecular weight of sodium? Yeah. Chloride? Well, the first two are easy. Did anybody get them? Ted?
For A,
Yeah?
80% moisture content.
80%. Mallory, you had B?
No, just
Okay. So yes. So 25 minus 5 is your moisture content. So 20 out of 25 times 100 is your 80% moisture. Okay, what about ash? What was ash? 20%. So you have 1 gram in 5 grams. That would be on a dry basis, right? 20% on dry basis. Now, the next one. Who has an idea of how to start? Billy has an idea of how to start.
You gotta find how many moles chlorine reacted and figure out it should be equivalent to how many moles of KSCN you have, right? And then you could, through your molecular weight, or I'm doing it backwards, but through your molecular weight, figure out your weight.
No, it's not KSCN. Well, it is KSCN, but what you have in excess is silver nitrate or nitrate. So you have 30 milliliter of silver nitrate in excess. So what you first need to know is the number of moles of silver nitrate total that you have. And then you'll find number of moles of silver nitrate. This would be that reacted with the cyanide. So then you need to determine the number of moles of this. You'll know how many of the silver was remaining that reacted with that because it's 1-to-1 ratio. So you'll know the number of moles of remaining silver nitrate. And you have the total. When you subtract that, you'll know the number of moles of the silver nitrate that reacted with the chloride. And because it's 1-to-1 ratio, then it would be equal to the number of moles of chloride, which is equal to the number of moles of NaCl, because NaCl is also 1 Na and 1 Cl. So you'll know the number of moles of NaCl. You can calculate the mass by knowing the molecular weight. I lost you? At least those of you that got it, start working on it. Where did I lose you? A long time ago? Okay. So remember, we add excess silver nitrate at the beginning. Portion of it will react with the chloride. The remainder of it is going to react with the potassium thiocyanate, right? It's telling you how much of this reacted. The number of moles of this will be equal to the number of moles of the remaining silver nitrate. Somebody said,
If it's a 1-to-1 ratio, would a blank would be 30 mils of both KGNO3 and ASCN?
No, this is the 30 ml that was added to the ash.
Yeah.
So some of that, if you convert that to number of moles, some of it is already reacted with chloride to give you AgCl. The remaining is going to react with the potassium thiocyanate. So first thing what I want you to do, get the number of moles of this and the number of moles of that. And look at the equation and think about it to see if it makes sense to you, and if it doesn't, I'll repeat. Yes, Ted, you have it?
15.66%.
What is 15.66%?
Oh, the original sample, never mind.
Oh. I haven't, not that far. Tell me number of moles of 30 milliliter of 0.1 molar silver nitrate. What did you get?
I'm answering for the final answer.
Well, the final answer require these.
Yeah. I didn't do the intermediate calculation, just put it in a big long equation.
Okay, so what was the final answer?
0.065%.
0.06.
Or wait, maybe that's 6.5%.
No, that's not the final answer. Lynn, what do you have? Do you have anything? Huh? 0.632%. Come on, Lynn, solve it on the board.
Yeah, when
Maybe a student will explain it better than I would. Talk as you go. Look at her.
go on this side.
Go in this side. We're all watching you, Lynn.
I calculate the total amount of the silver
How did you do that?
by, I use 30. So it's the volume times the molality.
Molarity.
Yeah. And it's,
I'm going to put complementary stuff over here.
and then I calculate the amount of this one used to titrate the remaining NA.
Molarity equal number of moles per liter. 0.1 molar is 0.1.
And this one equals to the amount of remaining silver. So this is original and this is remaining. If you get the difference, so the difference is the amount of silver you used to titrate the Cl in our sample. So the difference should equal to the more of Cl. So this is a more of, also equals to the more of NaCl, and we use the equation and mass equals more time by molecular weight to get the mass of NaCl.
Molecular weight.
Yeah, and this equals to 23 plus, and then you get the mass. You divide the mass by the total, the original mass.
Mm-hmm. Okay, I will restate what Lynn did. The first thing we do is we get the number of moles of this. So number of moles, remember, molarity equal number of moles per 1 liter. So I want to determine number of moles in 30 milliliter. Okay, so 0.1 molar is 0.1 moles per 1,000 milliliter. How many moles is per 30? So 30 times 0.1 divided by 1,000, I get the original total number of moles of silver. So that's the first part. The second part is I want to know what was remaining after silver was consumed by chloride, what was remaining? The remaining reacted with this, and it's 1-to-1 molar, 1-to-1 ratio. So I get the number of moles of this, the similar equation. So the 3 ml will have this much, 3 times 10 to the negative 4. The total is this much. The difference would be how much silver reacted with chloride. And because it's 1-to-1 ratio, then this, the difference would be equal to the chloride ion, the moles of chloride. And because it's sodium chloride, 1 sodium and 1 chloride, it would be equal to the moles of sodium chloride. So that would be, let me put these numbers. The difference would be 0.0027. So this much silver reacted with chloride, so I would have this much number of moles of sodium chloride. So I will multiply this by the molecular weight. I will get the mass. And then I take the mass, because of the original weight, I divide it by the original weight, multiply by 100, I get the percent salt. You can take a picture of that and the board and think about it. If you have questions, ask me again next time, because you never know if this is going to be on the final.
Then you never know.
You never know, so figure it out.